As a chemistry student, you've likely heard of the term thermodynamics, but what does it actually mean? According to the internet, thermodynamics is the science of the relationship between heat, work, temperature, and energy. Broadly, it involves the transfer of energy from one place or form to another. Chemical reactions, such as lighting a match, involve changes in both energy and matter. In 2012, about 85% of energy consumption in the U.S. came from burning petroleum products, coal, wood, and garbage. Of this, 38% was used to produce electricity, 27% for transportation, 21% for industrial production, and 10% for heating and powering homes and businesses. While these combustion reactions meet essential energy needs, they are also seen by the scientific community as major contributors to industrial sector emissions. Practical applications of thermodynamics are abound. Steam power plants is one of the most common thermodynamic application used in the industry. Steam power plants are important as an integrating application. The science of thermodynamics was born from a desire to understand and improve the earliest steam engines. Steam power plants utilize the principles of thermodynamics to convert heat energy into electrical energy. To produce the power plants, it undergoes the Rankine cycle process. First and foremost, a centropic compression process in which the water is pumped to high pressure and temperature. Next, heat addition, where the high-pressure water is then converted into high-temperature steam. Then, it moves on to isentropic expansion. The high-temperature steam expands through a turbine, performing work to drive an electricity generator. This process is continued by a heat rejection. The heat rejection process is where the low-pressure, low-temperature steam is condensed back into water in a condenser by rejecting heat to a cooling medium. Thermodynamic principles play a crucial role in the refrigeration industry as they govern the fundamental processes involved in cooling and heat transfer. Here are some key applications of how the thermodynamics concept works in refrigeration. Refrigeration systems consist of several key components working together to transfer heat, lower temperatures, and maintain cold environments. These components include the compressor, condenser, expansion valve, and evaporator. The refrigerant circulates in a closed-loop system, driven by a compressor. The compressor serves two key functions which circulate the refrigerant through the system, similar to how a heart pumps blood and compresses the refrigerant to a pressure that facilitates the phase change in the condenser. As the refrigerant enters the condenser, it surrenders heat to the surrounding air, causing it to condense from a vapor to a liquid. The liquid refrigerant then rapidly expands through a metering device, lowering its temperature. This cold, expanded liquid refrigerant then enters the evaporator, where it absorbs heat from the surrounding air, causing it to evaporate back into a vapor. The vapor then re-enters the compressor, and the cycle repeats. The closed-loop design allows the refrigerant to be continuously recycled through the system, without the need for constant recharging. The interaction of the thermodynamics laws is crucial for understanding the refrigeration cycle and its efficiency, where the zeroth law ensures the proper temperature measurement, and thermal equilibrium W. Heil, the first law governs the energy conversion and heat transfer processes, and lastly, the second LA Dewey explains the need for the cyclic operation of the refrigeration system and the inherent inefficiencies due to entropy increases. Together, the zeroth, first, and second laws of thermodynamics provide a comprehensive framework for analyzing and optimizing the performance and efficiency of refrigeration systems. To wrap up this video, it's clear that the application of thermodynamics in industries offers numerous benefits for both humans and the environment. Throughout this presentation, we've explored how thermodynamics can convert heat energy into electrical energy through power plants. Unlike petroleum, which is a non-renewable resource, power plants provide a much more sustainable solution for the environment. Without this knowledge, we risk increased pollution and depletion of resources necessary for future electricity needs. While this video has provided valuable insights, it only scratches the surface of the potential uses of thermodynamics in this sector. Thermodynamics guides the design of energy-efficient processes and systems that minimize waste and resource use. By adopting thermodynamically sound practices, industries can contribute to sustainability goals and reduce their carbon footprint.